Hi again. So today we'll be talking about what drives this process, what drives electricity. And first off, we're going to look at our outcomes. So these are, can we demonstrate knowledge, understanding and application of potential difference in the volt? I'm going to stop tapping the board so much, I'm sorry about that, it's loud, isn't it? Potential difference in the volt, EMF or electromotive force, not a force. Distinction between EMF and potential difference, or EMF, electromotive force and potential difference, and energy transfer in electricity. And these two equations, W equals VQ and W equals EQ, very similar, differ very slightly. So the first thing, we're going to answer this question, what drives this process? And the answer to that is slapping in front of you, the answer is charge, right? It stems from this two statements, like charges repel, so a negative and a negative push each other away, and opposite charges attract, to a positive and a negative pull together. So I've got here two electrons, we can imagine they're pushing on each other, go away, gladly, right? They're going to repel each other, they don't want to be near each other. Whereas, if we have an electron next to a large positive, that's supposed to represent like an ion. He's saying, come here, and she, anytime. It's sexist that I've made the big guy male. But in fact, don't focus on that. Sorry. Anyway, so we can imagine a load of electrons cramped up together in one location. Imagine an electron house. This could be like the negative side of a cell or a battery. They hate each other, they want to get away from each other because like charges repel. So they're going to push each other out of the house. Right? They're going to try and swell as much as possible. And they're over some imaginary wall, we have an empty house, the theoretically perfect location for them to want to get to. Not only that, if we strip all the electrons out of a thing, it inherently becomes positive. We can't take everything out of it, so if we take all the negative charge, it has a net positive charge left over. So the attraction for the electrons to want to go to that positive house is amazingly high. It's kind of like, you know, there's cheesy American films where you've got all the guys locked in one house and over a lake there's all the girls locked in another house. There's a huge amount of attraction, but there's a big lake in the way, and that lake serves a purpose, just like our wall serves a purpose. It stops the electrons just jumping across and filling up the empty house straight away. That wall prohibits them from making the manoeuvre they want to make. Instead, we make them go down predetermined paths to get to the end result. We let them get there in the end, but only after they do the work we want them to do. Now, the way we refer to these things is we say that this is at a potential, and we call that potential a number of volts. So we say there's a potential here, and let's say it's at minus 1,000 volts. We'll talk about what we mean by the volt in a second, but we'd say there's a potential there at minus 1,000 volts, and there might be a potential here of plus 2,000 volts. Now, as standalone things, that doesn't really mean a lot, but when we think about the difference between these two things, that's when we start to want to drive current. When there is a potential difference, current will flow if it can. So the potential difference here is, well, what's the difference between minus 1,000 and plus 2,000? There's a potential difference of 3,000 volts, where the volt is the unit of potential difference. We're going to talk about what we mean by potential difference. The definition of potential difference is the energy or work done. Sandy will be covering that in much greater detail in her half, but the energy per unit charge transferred by charge carriers. That is the definition of potential difference. So it's the amount of energy that each charge has. That's the best way to think about it. The energy that the charge carrier has, or the electron has in this case in a circuit, and that is going to be transferred by them into a different format. So we imagine that they have 6 volt cell here. There's got some cell with 6 volts in it. And as these electrons make their way through the circuit, before they encounter the bulb, they have a potential of 6. When they've finished after the bulb, there's nothing else in the circuit, they've used up all their energy, they have 0 potential. So we imagine saying that if we wire a voltmeter properly like that in parallel around our component, we imagine saying that the potential difference here should be 6 volts. So they have lots of potential beforehand, no potential afterwards. They've transferred the energy that they had into the component, and in this case a bulb. Now that energy will have been brought round held up by an electron in effect, if you can imagine it carrying the energy, which is a bad idea really to imagine it like that, but that's alright. So we take the electron, has some energy, it has some potential. When it gets to the bulb, it delivers that potential and returns to its original state. Now in reality, it doesn't fully run out of potential until it gets right back to the empty house that it's desperately trying to get to, which means that there will always be some energy lost in the wires, but very, very negligible compared to the amount in the components. Now, the electromotive force is measuring effectively the same thing. It's still got the units of volts, but it differs in this simple way. Electromotive force, EMF, is the energy or work done per unit charge, so the same as before, transferred to charge carriers, not by charge carriers, transferred to charge carriers. So this would be like looking at the potential difference across our cell. What is the supplied energy to our charge carriers for them to use up in the cell? So we can imagine our EMF is the supply, our potential difference is the user. From our definitions of potential difference and electromotive force, we can draw up 2 equations. And from that, we can get even more equations just by rearranging them. So, electromotive force, the work done per unit charge on charge carriers, becomes work done, or W over Q, energy per unit charge. From that we can write W equals epsilon Q, or work done equals the EMF times the charge. We can do the same with potential difference, or V in this case, most common one to refer to in our equations, is equal to the work done per unit charge. From that we can draw out the same thing. Work done equals potential difference times the charge transferred. Right? Hope that makes sense. So what I need you to do now is I need you to watch the additional video that I've placed in the haiku, which is about how to apply some of these equations and our other equations, such as kinetic energy, in real life situations and in exam style questions. So watch this video, watch the next video, and attempt those questions underneath. It's all written in the tasks that should be just to the side here, and it's all just below me here. So see you in class.